presentation, because indeed some speakers couldn't come to some presentation, and then they could watch this presentation on YouTube. So yes, so it's recording. Thank you very much, Peter, for reminding me.
Thank you, Sasha. Great to be with you all again. I wish I could be down there with you in person. I was actually just thinking the other day when the last time I was back down in Norwich, and it's been too long. So hopefully, when the current situation has calmed down again, I will make it down to Norwich and see many of you in person once again. I did look at whether I could come down today, but the journey planner was trying to send me via Amsterdam, which didn't seem like a particularly sensible option. But hopefully you can see my slides, and just before I dive into the content, I'm aware that obviously
yes,
this is obviously a special series of talks to mark Mark's retirement. So congratulations, Mark. Well done on all your years of service to UEA. On my own part, I just want to thank you as my PhD supervisor and everything you've done over the years for myself and my subsequent visits and subsequent times I've been back in Norwich. It's always great to see you, and I hopefully when I do get to Norwich again, you will still be around and we can catch up a bit more at that point. I took this photograph off the internet yesterday. So my supervisors were Mark Cooker and Adrian. If anybody doesn't know, this is not Adrian. I don't know who this person is. If anybody sees him again, we'll say hello at some point. But Mark, it's great to see you. Congratulations on your retirement. And yeah, I know hopefully Matt will catch up with Matt as well at some point in the future. I almost didn't recognize him when I saw the photograph yesterday. One of my contemporaries was a PhD student at UEA. Is now at Surrey. So let's get on with the content of this talk. And what I'm going to talk about today are droplet impacts with rough surfaces. So this is work that really I've been doing over the last sort of 18 months, 2 years during the lockdown up. So this is something my light relief during lockdown. Whether you think this constitutes light relief, I'll leave that up to you. In Aberdeen, I'm currently our Director of Postgraduate Teaching, and I think anybody who's held any serious admin positions in teaching-related jobs for the last couple of years have had a fairly rough time. So this was done as light relief during looking after all our MSc programs up here in Aberdeen. But it was really started off, it was some things I started with one of my PhD students, Nizana Ross, and it was actually something that we started discussing when Richard Purvis was last up in Aberdeen, which again, these visits have been too infrequent over the last few years. So I want to present some preliminary results. Some of this is currently under review at JFM, and some of it's completely not seen before by anybody. So as the purveyors of fine taste in fluid dynamics and applied mathematics, hopefully get some input from yourselves about some of these results today. And please let me know what you think. If you have any questions, then please just stick your hand up, and I'm monitoring the chat, and I can see you all in the meeting on my screen to the left. So just a bit of motivation. What I want to talk about is droplet impacts with rough surfaces. Now, this is an experimental photograph by a paper from Van der Veen, which is Detlef Loos group in University of Twente in the Netherlands. And this is interferometry results of pillars on a surface. So this is looking below, and you can see these sort of ring shapes here. And from these, you can infer the sort of shape of the free surface of the bottom of a droplet between some of these pillars. And in particular, this one, we have two sort of circular pillars here in the dark grey. And along this dotted line, you can reconstruct most of the black bit is the reconstruction, looking at the sort of the rings in this shape here. And then close to the walls, it gets a bit blurry, and we're not really sure what's going on because essentially the gradient is steep. The dotted lines here are essentially drawn by eye just to interpolate between that point there and the bit we can actually measure. So that bit is not really well known. Something to think about over the course of this talk. And then fundamentally, I'm going to ask what happens if I throw my droplet at a surface like this. So something with this sort of regular shape or some sort of shape like this. And what actually happens? How does that affect various features of the flow dynamics? Most of this stuff we've done for quite slow speed, and obviously I'm more interested in high-speed droplet impact. But what these things tend to be referred to, this kind of state here, where your sort of free surface is sort of sitting on the top of the pillars, tends to be referred to what's called a Cassie-Baxter state, where you don't have much penetration between the individual pillars. And then subsequently, you have what's called a Wenzel state, where you fully saturate the gaps amongst the pillars. And you can see how do you get from this position to this state, sort of motivating some of these ideas I'm going to talk about today. I'm not going to fully answer these problems, but it is by way of motivating what I am talking about over the course of the next section. So, contents of the talk, I'm going to think about 4 different problems. First of all, I'm going to think about a single droplet impact in some sort of asymmetric shaped substrate, shape to be determined. We'll talk about some examples as we go along. I'm then going to generalize that to a sort of pair of substrate elements. So obviously, if you think about those pictures I was looking at in the motivation, there are many impact sites there. Many is hard. I'll start with 1 and get as far as 2. And we'll stop at that point, I think. But it just gives some flavor, some of the features that you may be interested in these types of flows. So these first 2 problems, I'm thinking sort of smooth substrates, but then we'll go on to think about what happens if I have a discontinuity, almost a step in this substrate here. And then the final one, I'll think briefly about the sort of hole in the middle of the substrate. So what happens if my droplet strikes both sides of a hole in the substrate? And of course, what is the free surface? What does the pressure do? Any particular interesting features at sort of the contact regions and the like. Obviously, the step is sort of the half-hole problem to make life easier. So the problem 3 is sort of a stepping stone towards problem 4. So, few very quick assumptions. This is going to be done under sort of the guise of sort of Wagner theory. When I'm looking at high-speed, 2-dimensional problems. So I'm aware that this audience probably knows about as much about this as any audience I could probably find anywhere in the world. So I can quickly skim through this. There'll be a couple of slides in here for anybody who has not come across any of this before. But I think this audience probably is really expert in this particular field. But we're thinking about high-speed impacts. So we're going to neglect viscosity, we're going to neglect surface tension, we're going to neglect gravity. And 2 other things we're going to do, we're going to think about simple 2-dimensional flows. You can do some axisymmetric things if you have a sort of flat plate or an impactor, or even some simple 3-dimensional things. Obviously, if you have 3-dimensional substrates which look like essentially city blocks of vertical pillars, then that goes well beyond anything anybody can do analytically at that point. And I'm also going to neglect the effect of the surrounding gas, in particular the gas between the droplet and the substrate, although there are some places where that really shouldn't be neglected. But just as an aside, this is an experimental photograph from Sydney Nagels group from 2005. We know, for instance, if we reduce the air pressure surrounding a droplet, then in normal air pressure, you'll have a splash corona that comes up like this. If you reduce the air pressure, then your jets will come out sideways and just run along this flat surface. So we do know, even at a large scale, changing the air pressure has an impact on the various splashing dynamics. So we're going to think about problems initially in a frame of reference where the droplet essentially appears stationary in the far field, and then our substrate moves up from below and hits our droplet. So that makes life easier when it comes to formulating mixed boundary value problems. So but at a certain point, obviously, you want to present results in which the droplet appears to be moving towards a stationary substrate. So there are the 2 frames of reference here. We formulate these problems with the droplet being stationary in the far field, and we have a far field, a droplet profile here, which looks something like that. And we have some substrate, which is some function of position, and it then moves upwards with time t. So moving vertically upwards, and we'll have a normal impact with whatever shape we have and the droplet. We have a mixed boundary value problem because we have different boundary conditions on both what is the wetted surface, that's where the substrate and droplet are in contact, as a kinematic boundary condition, and then we have a condition on the displacement potential and the velocity potential as well. Primarily, I'll solve problems for displacement potential. I've done the calculations for velocity potential. There are some results in for pressure and loads and moments and things like that, but I'll mainly be showing pictures of free surfaces and the like. And then on the free surface, again, we have what is a kinematic boundary condition. These essentially come from the kinematic boundary conditions. And then there's a second condition here. This just comes from a linearized Bernoulli equation, essentially saying that this is integrating up the fact that the pressure is 0 on the boundary, and then integrating it twice to find that displacement potential is also 0 on the free surface. So we'll apply the same boundary conditions on the wetted surface and the free surface and all the problems we're going to look at. So I want to put them up front, and that's what we're going to be doing over the course of this talk. And just for those of you who haven't seen this sort of solution for the flow in a flat plate, there's our flat plate. This is a schematic diagram of this. A single impact site somewhere at the origin here, and our substrate is moving upwards at constant speed. What happens shortly after time greater than 0? You have splash jets coming outside of the droplet, and you have mass fluxes going out sideways along here. What we do is we formulate an outer solution, which then takes what's called the Wagner condition, which then has the droplet-free surface meeting this substrate at a point down here. And this is the sort of, I'll mainly be talking about the outer solutions to these problems. I'll spend a bit of time talking about the inner solutions in a couple of places. But we have an outer solution which essentially neglects the splash jet at this region, but this will give you an unbounded pressure profile at these contact lines. And to resolve that, we look at an inner region and some flow like this. What happens here is you have a dividing line somewhere here, and then some flow goes into the jet, and some flow goes below the droplet here. And this then translates along as the contact line B of t evolves. And just for the outer problem, the classical solution, if you have a half x squared as your undisturbed droplet shape, I'm scaling into a region here where I'm close to the bottom of the droplet. So the horizontal extent is always going to be much smaller than the radius of the droplet. And also, of course, when we start thinking about variations in geometry shape, the height of those variations is also going to sit primarily within this small Wagner region at the bottom, the outer problem at the bottom. So if you have a half x squared as your undisturbed free surface shape, then the contact line positions are plus or minus 2 root t, and there's a comparatively simple form for the free surface shape as well. So that's by way of background, and now let's talk about what happens when we generalize this and think about a case we don't have a flat plate. As I said, sort of the vertical height of this substrate sits within this outer small region, so that does place limitations on how much vertical extent we can have here, and also it does place limitations on the gradient of the body at these various points. But we'll sit again in a frame of reference where our droplet appears stationary in the far field, and then our substrate moves up vertically to impact the droplet. And then we have an impact site, x0, y0, and sometime after impact, we have a wetted region between A of t and B of t, where depending on the geometry, we want to work out what the free surface is out here, what the A of t are, and what B of t are, and how they actually evolve over time. And the substrate here, I take some scribe substrate geometry and think about what these solutions actually look like. So I've written down the mixed boundary value problem in full here, but this basically recaps what I said in the previous slide about the various conditions satisfied on the wetted surface and on the free surface. We're essentially solving Laplace's equation either for the displacement potential capital phi or the velocity potential little phi. I've tried to use bars here to represent the quantities in the frame of reference for in which the droplet appears stationary in the far field. And there's a corresponding unbarred little phi and unbarred little h, which are the velocity potential and the free surface position in a frame of reference where the substrate appears stationary and the droplet is then moving towards the substrate. What we do, and again, this is familiar to many of you, is that we formulate this by using Cauchy's integral formula. We have something like this, where we have a function lambda. Lambda in this particular case, because we have this asymmetric impact sites, we have to be careful that obviously there's no reason to suppose that A is equal to minus B, which you would have in a symmetric problem. So this is a generalization of the sort of the flat plate function. And obviously we're looking at the upper half plane. We drop this onto a half space. We have a mixed boundary value problem formulated on the half space, and our A of t and B of t are found as parts of the solution. We have an asymmetric problem, so in order to guarantee that we have bounded solutions for the free surface, the contact line, we're required to solve a couple of consistency conditions. So again, this comes from thinking about the contour. This is the contour in the upper half space. It's a semicircular contour in the upper half space, which runs back along the x-axis, and we apply the various boundary conditions to the various regions, taking a lot of care to work out which bit of which bit of lambda, applies to the various bits of the interface. And we have two conditions now because we have an asymmetric problem. If you have an even body, an even impact, a symmetric impact, you only have to solve one consistency condition. So they are two consistency conditions. The first one is the sort of well-known one you'd have for a normal impact, a symmetric impact. And the second one is the fact you get because you have this asymmetry. In particular, if you have a symmetric impact and potentially say S of X, your geometry is even, then what happens is that A does equal minus B, and essentially this second equation is automatically satisfied by taking S of X to be an even function. And then that simplifies quite easily just down to this one problem here. This is the corresponding free surface shape. Again, the geometry sits in here, but in a very simple case where S of X is 0, in that case it's obviously an even body shape, so A equals minus B, so that integral disappears. A equals minus B, that term will disappear, and again you can see quite x0, the impact site is 0, the origin, and you can see you can actually recover if you're familiar with the solution I wrote down for the flat plate. So the flat plate solution is inherent in here. It's just adding the geometry in to actually look at various different shapes as well. Oops. Some solutions, a couple of quick solutions. This is kind of a test it's working sort of toy problem. If you have an impact with a sloping plate, then all you're doing, actually the contact line velocities don't change. So you have the 2 root t associated with these. You shift the impact site slightly up the slope, but there's no change in the pressure profiles. These 3 pressure profiles are identical. I should say these are the outer solutions, so that you have to regularize, do something here to make sure you don't have a unbounded pressure. This is where the splash jet comes in. I'm just plotting the outer solutions here. But essentially what actually happens in this case, very simple case, is you just shift the impact site up you move it up the hill slightly. As you increase the gradient, you shift it more to the right in a fairly sensible way. Second type of solutions impacts with a second cylinder. So I've approximated that by a circle here, and then there's a shape parameter k, and then the offset c. And again, in this case, you can write down the contact line evolution position, and the corresponding free surface shape is there. And you can see the various examples. There's a sort of normal impact. Sorry, there's a symmetric impact, and then as you shift the offset, you have to lower the droplet, sort of descends further before actually impacting the substrate. I should have said actually at the outset, I've set these things up so time t is 0 at the first instant of touchdown. And you probably remember there's a factor h0 floating around in my droplet shape. That just lets you move the droplet up and down. So at time t equals 0, that impact is, you do actually have touchdown at that point. There are obviously other ways you can scale these things to translate coordinate systems to do things slightly differently, but this is the way I set it up. And I want to compare this to some double impacts in a second, which is why I've set it up in this particular way. They were the easy ones, they're the sensible solutions. And let's talk about a set of solutions I'm not really very happy with, to be perfectly honest, and what can go wrong if I try this type of thing. And here's a case where let's think about a finite step. So this is a shape that looks something like this. There's a sort of height, h, the vertical distance here, and then there's an offset, c. Now I can do exactly the same calculation. I can follow through, do the same thing I did before. There are a pair of consistency conditions. They're obviously now horrible, and you can't write down analytical solutions to these things, but there's nothing stopping you solving these things as a pair of nonlinear algebraic equations. Obviously you do it iteratively. You need a decent initial guess, but you can usually find a decent guess, and you can actually work out how these solutions behave, and you solve these this algebraic, nonlinear algebraic pair of equations at each time step. And that will tell you what the contact line positions A and B actually are. So I'll just show you some contact line evolution positions. The left is the position, and the right is the velocity, and this is varying step size. This outer dotted line is the flat plate solution, and you can see it initially starts, this is the A contact line to the left of the slope. C here is 0, so it's actually hitting on the edge of the slope, and then it moves much more slowly, and then after it eventually starts to move along that below the bottom region of the slope here. You see the corresponding outer solution, the corresponding contact line for the right boundary over here. And then obviously as the step size gets bigger, you move in that direction. So it takes longer for this left contact line to actually start moving away from the site of the step. It's perhaps a bit clearer if I actually show you the free surface profiles in this case. So we have a finite step. The top row is essentially shifting the offset c, so that's moving this step to the right. And the bottom row here is just adjusting the site of the step. And actually, you can kind of suggest here as the step height goes to 0, you get back to your flat plate case, which is exactly what you'd expect. Now, I look at these solutions and I ask the question, is that really physically sensible? I'm not really sure actually they are. I want to put them up, but I'm a bit concerned about what actually happens at the inner edge of this step point here, and whether actually, if you look at these solutions, it automatically wets the full vertical height of the step and starts to wet the region down here. So the wetted surface is that region up the side of the step and that region up there. That is the solution you generate. But if you think about the picture I put up at the beginning, the experimental photograph, we know the picture looks okay. Obviously, this is between essentially a hole here. So we have two steps, but think about the left hand to the right hand side of this. We know what the free surface shape is doing, we don't actually know what goes on in this region here. I say this is inferred by essentially a linear interpolation between that end of the point we do know and the top of that corner here. It might be that the surface bends over down here if you're going, but I'm unconvinced by that. And I kind of think you probably will have your solution pinned here, probably until you exceed some certain contact angle, and then it will gradually start to descend into this hole. But I mean, that's something just to have a think about and maybe ask some questions about at the end. I wanted to put these in as sort of things nobody's seen before and get some feedback from you, see what you think about these as solutions. And I'll say more about steps later on where, of course, these step heights are still within the Wagner region, the height. But you can also imagine steps which are much bigger where I don't actually have this bottom flat plate along here. So I just have this left-hand side and then disappearing down here. So I'll have a look at some solutions that look like that as well later on. Right. So problem 2, we generalize this slightly. And now we think about solutions where I have symmetric impacts and we have 2 impact sites at x0 and y0 and minus x0 and y0 are substrates an even function. So after time t equals 0, we have wetted surfaces between minus b and minus a, and between a and b, with the substrate moving up vertically, and in our far field, our droplet is at rest. The mixed boundary value problem is essentially the same, except I have some absolute values here to account for the fact I've got these double wetted surfaces in various different places. That's the only change, I think, on this bit. Obviously, this characteristic function which goes into the integral equation is more complicated now, and a bit careful about working out what is the appropriate route for as you go back along the axis. But it all works out okay. You still actually have a pair of consistency conditions because of the symmetry. You might expect you have 4 conditions now, because you have essentially 4 roots, but of course 2 of those roots are the same in each, also minus each other, and then various symmetry conditions mean that you're left with just a pair of consistency conditions. So what I've got there, for given geometry, again, I have a pair of equations in order to find A and B, the contact line positions, with the knowledge, of course, that minus A and minus B are also the contact line positions for this problem. Then we've got the free surface shape. Well, again, I can plug in my geometry and think about what the profiles actually look like. So what I wanted to do is actually compare some of these double impacts with the corresponding impact with just with just the right-hand side of the substrate. And it's gone very dark, I mean, to turn my light on. So the reason for doing that is just to think about, if you want to build a substrate with these shapes on, what we'd like to do is actually deploy these in higher speed applications than they're currently used. They work well in sort of lab experiments for impacts up to sort of 1 or 2 meters a second. But if you wanted to, say, deploy them on the leading edge of an aircraft for sort of aircraft ice mitigation, and your aircraft is merrily flying along at sort of Mach 0.8 and it suddenly hits a raindrop minding its own business, then obviously your impact speed is much greater. Your droplet will probably get shredded in the airflow before it hits the leading edge of the aerofoil, but various bits of droplet will impact your aerofoil. So we want to think about what are the loads and pressures on these surfaces as you actually calculate as in these double impacts, and how does moving sort of 2 impacts, two elements of your substrate apart, how does that then change the pressures and the loads that you actually experience? So it's a really awful calculation. You can find the velocity potential for the double impact. You can then differentiate it to find the pressure, and then you can integrate it again with respect to space to find either the load or the moment here. The load is simpler than the moment, but even that involves ratios of complete elliptic integrals. So this is a really awful calculation, but I'll show you the results. This is the sort of thing you should never put in a presentation. I've not put the moment in, I've not put the pressure profile in, but you can, in principle, write it down. It's horrible, but you can. There's nothing stopping you doing it. And there we have some results for the first geometry to think about, which is y equals some constant times the absolute value of x. So this is the interior of a wedge. You have a droplet hitting the interior of a wedge, and the question is, what are the contact line evolutions and what are the free surfaces? So starting with the left plot over here, there are two values of k, obviously corresponding to the gradient of each side of the wedge. And there are two impact sites. So you have B minus A on the orange lines, then A and B on the as the four contact regions here. And these thick lines are the double impacts of sites with in the symmetric in the wedge. And then these, you can see that the thin dotted lines here, that is just the corresponding right-hand impact on a slope y equals kx. And obviously, with double impact, you want to ask the question, how does your double impact contact line evolution differ from the problem I looked at previously with just impact on a sloping plate? And you can see the inner contact line moves towards the center more rapidly and moves away from the center. The outer contact line moves away from the center more slowly. Because I've neglected air in this problem, the inner contact lines can actually come together. And there's actually fairly simple results which tell you that the time t1 when this happens and the corresponding outer contact line position. You essentially have to solve those two consistency conditions for the problem when A is 0. But in that limit A equals 0, your elliptic integrals will have nice expressions in terms of pi, so you can actually write down those things. So that's what the dots are here. And after those dots, you have a single wetted surface between minus B and plus B, and then you can just do a standard symmetric single wetted surface impact problem, and then you can continue the contact line evolution after the point this initial inner region has been filled up with liquid. The corresponding loads and moments are on the right-hand side, and again, they're compared to the dotted lines of the case with the single floating plate. So that good thing to note is these horrible formula for the load and moment, they do get you back to the impact case for a flat plate, at least at the very small times. When of course at very small times, then this left impact site doesn't know much about this right impact site, and you can see there's a good agreement here between this double impact and the corresponding single impact with the sloping plate y equals kx. So I was quite pleased. Well, you do this horrible calculation, find this answer, and then you decide, okay, well, the answer is exactly what I expect it to be from the flat plate case, but actually on reflection, that's fairly obvious. These solutions, these loads and moments, then blow up as you get close to closing the gap between the inner contact lines. And just quickly looking at the corresponding free surfaces, this is just half of the droplet here. There are two sets of colors here. The blue dotted lines are those regions before the inner surface here gets filled up with liquid. And then this red dotted line is the dividing line at the point where the free surface makes it down to the origin here. So there's no longer essentially a void underneath this droplet. And then you can continue with the various free surface shapes computed after that time. The free surface profiles, again, something I probably shouldn't write down in the presentation. I'm trying to fit how many elliptic integrals I can fit into one presentation today, so I apologize for that. It's a pretty awful formula, but it does give you these various wetted free surfaces. And of course, you're going to have to calculate, as I said, the values of A and B numerically in these cases. there is the corresponding pressures. I'm not going to spend too much time talking about pressures. I'm a bit conscious of time. I will say one thing, obviously you need to calculate contact line velocity in order to evaluate pressures and loads and moments. I didn't actually integrate, I didn't actually differentiate the consistency conditions in order to integrate them with respect to time in order to find the contact line evolution. They were done, as I say, by solving nonlinear equations. But obviously, if I know what A and B are, then I can write down this system, this 2x2 system, which will tell me what A dot and B dot are, the contact line evolutions. You can't actually integrate these starting at t equals 0 because the initial velocity in most of these cases is unbounded. So as something to numerically solve these equations, you can't get the full contact line evolution from this because without doing at least some more work here, because you say your velocities are for t equals 0 turn out to be unbounded as you expect if you've seen the solution for the flat plate case. You can, of course, for verification and things like that, once you have a position, once you've solved the nonlinear equations and found a position on the contact line, you can use that as an initial condition to integrate these both forwards and backwards in time to get the full contact line evolution and verify that your nonlinear solvers are doing what they're supposed to do. So that's all been done by way of checks. The next profile, I'm going to skip over this slide. This is essentially very similar to what I had before. So now I'm thinking about a pair of cylinders. I'm not going to describe this again, but the same kind of behavior is seen here. But then what I'm going to do is just show you the profiles. It's a little bit small, but hopefully you can see that where I have essentially two cylinders in grey here. The blue lines are the case where I have both cylinders present, and the dotted red lines here are the case where just the right cylinder is actually present. So then you can see as I move the cylinders further apart in this right-hand case, you can see that actually I get closer to the, at least locally closer to the case where you have the double impact, and you can see the sort of symmetric, in the blue shapes, it's symmetric about x equals 0. Velocity potentials and pressures are also calculated, and again you can see as these cylinders are moved further apart, as you'd expect, the impact, the local behavior on the right-hand impact site gets closer to the problem you have with just a single impact. And of course that's just because as I move the cylinders further apart, the right-hand impact knows less about what's going on over on the left-hand side, and that's what you see here, and ultimately, and the pressures look very similar if I move them this far apart. Obviously, if I run this for longer and let this infiltration in between these cylinders get closer together, then the A will get closer to 0, and I will start to see more deviation, like you can see down here. Another horrible expression for the free surface profile, but I say I have done some calculations here, and that is the very horrible answer you get out of this problem. And then finally, before I move on to think about steps with bigger steps, I want to think about sort of alternative or what happens next. Because obviously I've talked about one impact site or two impact sites, but most substrates, obviously rough substrates, hydrophobic surfaces, have many pillars, many features. And this is essentially what happens next. So the blue lines here are the profiles, and if you imagine that rather than having a pair of cylinders, I have an array of cylinders going along like this, then this calculation stops when I have a sort of secondary impact site here with this next pillar or next cylinder along the array. I've still got a void trapped in here below the the initial impact site, and there's a second void going to be trapped in here. And that's just due to the height of this geometry. As I change the height of the geometry, different things can happen. So here I have a case where I filled in the initial region beneath the droplet, and that's the profile at the red line. And then I can keep calculating additional profiles from a single impact site between minus B and a single weighted surface between minus B and B, and they are the corresponding profiles you get for this single wetted surface. and you have a secondary touchdown on this second pillar here. And again, you then have to do some more work at that point. And then the final option, if your cylinders are, your K is smaller, then what happens, you can get down to this point between this cusp between this first cylinder and this second cylinder without actually impacting this second cylinder. And then obviously you can keep calculating these solutions. You know, your free surface, your substrate shape is then that first cylinder and probably part of the next cylinder, and you can keep going along like that. I'm conscious of time, running out of time a little bit. So I'll move on and talk briefly about what happens for problems with steps. And this is a case where obviously geometry I've talked about previously had the vertical extent of that geometry within inside this outer problem, outer region. But you could quite easily imagine cases where if you had very tall pillars relatively, then the droplet doesn't know in this region here, when you really sort of localize onto this, look close to the bottom of the droplet, it doesn't actually know that there's some base potentially down here. So in terms of the outer problem, what you see is just the tips of the tower block essentially, and you don't know what's going on between these spaces. Now, I've drawn this picture over here. Again, this is the cartoon where it looks like I've pinned the solution at this contact line here, and that's one of the issues you have to think about in these types of problems, where you have a single weighted surface, then just wetting between C, the position of the edge of the step, and B of T, this contact line, which then evolves in this direction. So first question is this a good sort of cartoon picture of what actually is going on? And my first comment is, well, no, it's not, because of course this is still an asymmetric problem. I will have two consistency conditions to solve here, and of course C now is fixed. I don't get to pick C. C is imposed by the geometry, so that leaves me two consistency conditions in order to find out what the value of B is. And at that point, that doesn't work. So, of course, the reason I have two consistency conditions is that I've imposed the fact that I have bounded solutions at that point there, and I have a bounded solution at that point there. To generalize that, I can think about cases where I don't actually have a solution which is bounded at both points. I can think about a solution which is just bounded at one endpoint rather than being bounded at both endpoints. So I can't have an unbounded solution at x equals b, because obviously there's either droplet or there's substrate in the way. But I could have an unbounded solution at, well, just to the right, just the left, sorry, of x equals c. So I can look for solutions which are unbounded at this point. And then the cartoon I want to think about is something that looks like this, where I have my free surface, and then I've wetted this whole region along here and down the side of here, and I have a liquid shooting off down here. Now, of course, for practical purposes, I don't believe that you do have this liquid jet, whatever it is, shooting down the side of your substrate. But I need to put that in there in order to make sure that I can have enough consistency conditions in order to find, well, I have not to have too many consistency conditions so I can actually resolve what B of T actually is. And then the idea for this, and there's some details here that I'm not going to present that needs still working out, but the idea for this is there is then a local solution about this step edge which resolves the fact I don't really want to have this jet floating down, shooting off down here. And there's some very similar ways that you have an unbounded pressure at the outer contact line you resolve by looking at a local behavior at the contact line here to find the jet. I envisage something similar going on at this point here to resolve the fact I don't really want this jet in this direction. I of course want a jet over here, but not this one. So that's what I'm going to do. I'm going to look at some outer solutions. I'll say a little bit more about the inner contact line, the inner problems at the end of this section. I'm running out of time. There's the mixed boundary value problem. The characteristic function now is chosen so that I'm guaranteed to have bounded behavior at B and unbounded behavior at C. And there are two possibilities. I can have a negative C, which means the step is actually to the left of the lowest point of my droplet. And so for that reason, for that that case, that's not the picture I drew, but you can imagine a case where the step is to the left of your lowest point on the droplet, and therefore the droplet will hit a flat plate initially up until a certain time. You have the flat plate profile, and then your contact line region, your left contact line will eventually reach that step and will fall off the edge of that step. So there's two types of solution behaviors present here, and that gives you the contact line position for that. And then corresponding to the case I drew, there's a single consistency condition, and you have a contact line evolution, which is this. Contact line evolution, some pictures. The black line here is the classical 2√T solution for the flat plate. And then moving down in this direction, these green lines are these profiles where C is negative. So it starts off following the flat plate solution. And then when your contact line reaches the step, what happens next is that when your left contact line reaches the step, the right contact line motion then slows down, and you can see it then moving away slower than the flat plate contact line solution. The dividing line C = 0 is the line where the step is directly below the bottom of the droplet. So that's the dividing line in these cases. This dotted line here is the line √2T. So that's the position of the droplet if it didn't deform and just carried on moving horizontally without actually hitting anything. And of course, you start hitting things when C = 1, then you have the step here moving more rapidly than as it deforms. I've shifted the time origin here, so rather than the time t = 0 being the case when you have impact, t hat = 0 is the point at which the droplet first descends below the height, the upper level of the substrate. And there are some solutions for these types of problems, ignoring the fact that we're dubious about what's going on at this point, just to the left of this step. But one thing to note here, you can see this is this case where C is negative. So this first region between this dashed dotted line here, that's just the Wagner solution for flat plate impact. Obviously, the contact line moves over here, and then when it gets to this point, the contact line is no longer supported by a substrate over here, and it will fall away down the side of this step. And you can see various profiles on both sides here. So I say a little bit about the contact line, about the inner solutions, and I'm not going to do any more details about this because I'm running out of time, and I have some solutions, but none that I'd like to present to anybody at this point. But what you'd imagine, region 1, you can imagine the turnover region. You have exactly the same local structure in this sort of jet route here. The height of the jet will be modified because you have a slightly different outer solution. The velocity potential in the outer field is different. So when you match your inner solution to the outer solution, you'll end up with a different mass flux going into the jet. And in a similar kind of way, what I'm hoping to see is some solutions close to this contact line. These are still work in progress, where you can imagine you start evaluating the contact line, the contact angle at this point. I probably think you have this kind of structure where you go to you have a essentially continuous profile here, but you might end up with cases where you have ultimately your free surface starts to descend below this. I guess you start with this, and it'll probably tend to this if your angle here gets small enough in the way I've drawn it. So then it will start to descend down here. You still might have some jet going down the side of this step, but I don't tend to believe that's a sensible looking solution. And I say that's the picture we've drawn. I've shown you already in a couple of cases. Very quickly, I've got 2 minutes left, so I'll just go for the whole case. This is like the jet, like the step case. Rather than thinking about a picture like that, I'm thinking about pictures where I have unbounded solutions between on the insides of these holes, inside of these holes here. And again, I haven't done the calculations again, but the same issues are going to apply to have local solutions at the inner step, the sides of the holes, just to sort this stuff out. contact line, mixed boundary value problem, characteristic function, all of that's the same as before. Velocity, contact line evolutions. You don't obviously have the cases when C is negative, because that doesn't make physical sense to have a negative hole width. But you can see these cases where the hole suddenly starts to get C bigger than 0, and you can see these various evolutions of the contact line positions. And there are some corresponding free surface shapes where you can see these solutions are unbounded just immediately to the left and right of these contact lines. So something has to be done to resolve those. But you can see as the hole gets larger, the contact line moves away on the flat surface more slowly, which is physically what you'd expect. And of course, you can calculate other quantities, things like penetration depths and the volume in the hole. One final limit, and I really am done, is to think about what happens when C equals 0, i.e. your hole thickness is very small in this outer solution. You do recover a nice simple contact line evolution, but the thing to note about this is not 2 root T. So this is not the problem of a flat plate. There is genuinely a hole of minuscule thickness at x equals 0, but the contact lines are not moving apart at the same speed as you would have if there was actually just a plain flat plate. And the contact line solution is here. Actually, if you think about B of t being, if it was 2 root t here, then obviously, if you look at this carefully, you'd actually recover the solution for the flat plate if this B of t when c equals 0 was 2 root t. But it's not actually. B of t when c equals 0 is this, so you get something slightly different here. And again, what's actually happening here is that the volume in this hole is essentially a mass sink at the origin. And because you have a sink of mass at the origin, that means the outer contact lines don't move apart quite as quickly as you'd expect for the traditional flat plate. So I was just saying, there's a sink at the origin which moves things apart, which drains the mass from the droplet. And then I'm done. So that's quite a rapid run through, probably too much material for a 1 hour presentation. So I do apologise. But if you do have any questions, please let me know. Like I say, there's some very rough edges towards the end of that where there's some work in progress that needs sorting out and finishing. But if you do have any questions, drop me an email, or I'll probably stay around for a while and have a chat. It's good to see many of you again. So thank you, everybody. Thank you, Sasha.
Thank you. Thank you very much. Thank you. Frank, your question?
Yes, thank you. Very nice talk, Peter. Great stuff.
Thank you, Frank.
Could I just ask a couple of related questions for the hole or the step problems, which are always difficult, aren't they? One is, would it be helpful at all to tackle a step with the corners being smoothed?
So I did some. I have some solutions that look like that, and you don't actually. This is where you've got. I did look at some solutions like that when I was doing the smooth body shapes. That was my starting point. I actually started with the step and realized this is pretty horrible. Let's do the smooth problem first, and then think about what happens in this step case. What will happen is if your body deviates or goes around a corner and smoothly transitions to this sort of vertical plate, I just looked at sort of parabolic edge steps, so flat top, quadratic edges, rather than going to purely vertical edges, because that makes the integration slightly easier to deal with. And there's nothing stopping you doing that, but as your body shape gets steeper and steeper, then the contact line obviously moves more rapidly down the side of the step. And at a certain point, I'm just wondering what goes on when you do have that corner, whether you pin the free surface there or not. And this is something I haven't worked out. And the experiment, that's the interesting bit of the experiment, is obviously the bit you can't resolve because the camera doesn't get right into those corners quite as much as you would like. So the interferometry pictures of the free surface I presented, I showed, not clear what goes on in that corner. So some more work needs to be done just there.
Yeah. Okay. So the second point was is a downward jet definitely not on? Do you think?
I don't know. No one's ever seen one. There's no pressure. So the pressure at that corner goes to 0 in the outer solution. So I don't know what drives the jet if it does go down the side there. Again, it might be there and we haven't seen it yet, but I kind of suspect it probably isn't there, and you have to think more carefully about that corner. I'm open to suggestions. I don't know if anybody's thought about this or considered it elsewhere, but it could be there. My gut feeling, and it is literally a gut feeling at this point, rather than any strong view one way or the other.
Sure.
Is that probably it is pinned or something goes on in that corner.
Possibly some experiments would be helpful, to see how it's what's there. Yeah, I mean dedicated experiment.
Thank you.
Hilary or John? Hello. There was a question from Hilary and John. No?
Is it on mute?
Unmute. Okay.
There we go.
Yeah, now it's okay. Yeah.
I've gone back to mute again.
Okay.
Oh, I see. Right. Is it okay now?
Yes.
Perfect.
Yes.
Right. Yes. This you're having these troubles near these corners, but right near the corner, isn't it like a wedge entry problem, where you have a semi-infinite flat liquid with a wedge coming into it, which is a fairly classical free boundary problem, isn't it?
Yes, in that case, I guess you would be looking at a jet down both sides of the.
Well, there's a sort of.
Depends.
Well, there's a wetted region goes down each side, yes, but there's a great deal of literature on that and the sort of angles that the surface makes with the wedge. Edward Frankel, I think, did a lot on it, and Bryce McLeod, but it's been around. It's in, I think it's in Burkhoff and Zarantanello's book as well. So I think that can tell you all about what's happening right at that corner at the initial time, and that would be very reliable information. And then your solution should match back with that as time goes to 0.
Yes, that's helpful. Thank you, John. Yeah, I'll think about that.
Yeah. Also, I just a passing thought. If the roughness length scale is, say, much shorter than the droplet size, you could do a Wagner theory with a sort of Beavers-Joseph boundary condition on the base, couldn't you? That would be a sort of homogenized version of it.
Yeah.
Absolutely. Again, that's something that I haven't done it, but people. Yeah. Actually, you've done something on initially.
Not me. But
wedge entry.
But I did, but it's still within the Wagner theory. So it means that roughness and perturbation, they are still smooth and small. Smaller roughness. So it would be very interesting because we do expect that if the scale of roughness, as John said, the smaller than scale of our problem, then the roughness can be accounted by some modified condition or something. But
that's what I said. Beavers-Joseph, I think.
Yeah, but I don't know how to do this. I mean,
it's a relationship between the flux and the pressure somehow.
1967, I think.
Yeah, I don't know how to do this because this means to start with the kind of general problem, everything included, and then by averaging procedure or something to come to that. And also, kind of my addition to first comment from John. That yes, initially the wedge impact problem, actually oblique wedge impact problem, it's relevant, and it will give the initial asymptotics. But later, when the scales are different, it's likely that your solution is applicable. But then there should be some matching between these two solutions. So this is, again, I don't know how to do this.
No idea.
We
did use beavers. Richard and I, we did a paper on, it was a gas cushioning problem on porous media, and we did put beavers Joseph on that, but it was on the bottom of the air.
Oh,
So
no.
we've done something with the air present, but not on the Wagner, on the boundary condition on the liquid itself. So
yes.
I see Mark just put a comment in the chat, and I will try and look this up and see what he actually says.
Yeah, this condition is for porous. You are right.
Yes, but for porous, it's all porous.
Yeah, but if it's John, if it's not porous, it is just a roughness. So if the air is not important, so then another condition should be there. It's like it's a very turbulent flow because of roughness, you know, with many vortexes, with something. It could be local high viscosity flow. I don't know.
The viscosity will be important on this very.
Yeah, but how to do this? No idea indeed. But it's very interesting problem, but very tough, very complicated problem. Yeah.
Also, Sasha, I have one general comment which I'd really like to make to everybody when you've finished with the mathematics, if I could.
Yeah. Yes, please.
Well, I raise it if there are any other mathematical questions. Do that.
Okay. So I have a question, mathematical question, kind of mathematical question. Peter, you did your analysis, but I'm not sure that you always kind of respect the condition that the, say, dead-rise angles and angles between surfaces should be small. Is it always can be satisfied? What's your opinion on this? Is it always possible to say that, yeah, for certain conditions the dead-rise angle is small?
I am pushing at that. I am pushing quite hard on that condition. I think you're okay for the smooth bodies, because that requires, obviously,
yes,
that requires initially the tangent of the surface. It's
problem with the corner point.
Yeah,
but not necessarily a right angle. It can be any angle, by the way.
Yeah.
It could be small angle, you know. I mean, small deviation from pi. Then it could be fine, right?
Yes, I mean, if you have a small deviation, then you can obviously you have an asymmetric problem.
Yeah.
I don't see any. If your angle is small enough, then you're fine to do your dead-eye angle is going to be small enough. You're fine then to do a deviation from a flat plate. I didn't do a flat plate onto a slope. I have the solution for the wedge the other way up. So you hit the point of the wedge, and obviously it comes down both sides of the wedge. And that, of course, if the gradient of your wedge is shallow enough, you do have kind of that sub solution.
Okay, we have a question from Robert. Robert, please.
Hi, Peter. Lovely talk.
Thanks, Robert.
So, was I right in thinking that when you had your two cylinders, and you compared that to the solution you got when you just had one of them present, that the contact lines on the one that was sort of there in both cases sort of shifted towards the one that you'd added?
I'll just plot the picture again, might be a better way to do it. So we just this one, Robert. So you were saying,
yeah, there was one before with your like A of T and B of T on a couple of slides before that, I think.
Slide,
yeah, that one. So the sort of red curve on the right hand side.
Yeah.
So the solution with two in is to the left of the solution where you've just got one.
Yes.
And that to me seems so on the inside bit where your mouse is, that I could believe intuitively. But my intuition says that if you add a second one that's kind of pushing the fluid to the right hand side there, it might make that contact line go slightly faster.
So what actually happens though, if you look at the free surface profile, you start descending, more fluid gets sort of pulled down between the two cylinders. So you're quite a long way below the the single free surface.
Yeah, I could kind of believe that there, because the second cylinder is kind of forcing fluid into the right in the middle. So the middle bit I can believe. That the other side, if there's any effect from the second one, I would have expected it to push more fluid to the right, and therefore for it to get further. And I'm wondering why my intuition is wrong. And if you've thought about sort of what's going on and what's affecting it, or if you can understand why.
The short answer is probably no, although like I say, there's a lot of fluid that's got further down between these two cylinders here.
Yeah.
And obviously you have that fluid has to come from somewhere.
Yeah, suction. Like
so I think it kind of pulls it over the top of this, which it does look a bit odd, right? Yeah, I fully agree with your intuition, Robert, that you kind of expect it to spread out more on both sides in this case. But I think it's just the case that in this particular problem, you've pulled so much fluid between these two shapes that fluid has to come from the outside regions here.
So you do conserve the total volume.
Yeah.
At that order.
Yeah.
Okay, so maybe my question is, why is it pulling down so much in the middle?
Yeah, that's moved the question on.
That might be the question to ask.
I mean, the thing about the middle is obviously you have to satisfy a symmetry condition at x equals 0.
Yeah.
Whereas if a single impact, you can keep going. You have an upwards gradient immediately always to the left of that inner contact line, and so obviously you've got to bend the free surface over to rather more. Although I need to think about that one a bit, I think.
Interesting question.
Cool, thanks.
Interesting question. Yeah. Some suggestion, Peter. At the beginning, you showed that 4 problems, and it's I believe would be reasonable to add problem number 5 with so-called periodic impact, where the many cylinders and you consider just one period. Yeah, just one period. Okay, let it will be smooth cylinders, so no problems with dead angle like in problem 2. But then there are flat free surface.
Yeah.
Impacting on many cylinders.
Yeah, I think Frank did that problem in the paper with Andy Ellis and was it Andy Ellis and Ellis and White. There's a transformation. Frank, do you remember that paper in Journal of Engineering Maths? No, I don't know where it went exactly, but there is a solution
periodic impact,
for periodic impacts.
Yes, yes. QJMAM maybe.
That sounds about right. Yeah, so it's in there, and there's a control mapping to put you into a strip between 2 lines of symmetry on either side of the either side of a single wedge. I have got some numerical solutions for more than 2 impact sites for water entry problems. So sort of periodic numbers of solutions, but that obviously you have to then solve rather more nonlinear equations, and therefore you need rather better initial guesses to actually find appropriate solutions. And they're not fit for human consumption at this stage. But I mean, I did have a look at that kind of problem, and obviously there is this large limit where you do approach symmetry, this periodic array at the other extreme. So it's on the to-do list.
Yeah. If no any more mathematical questions, then John, you want to
this is an amazing opportunity because there are so many Wagner experts sitting together here. Now, I expect, like me, you've been reading in the newspapers about the Stark effect, and Stark, who was a Nazi, had a big effect on physics. Of course, Wagner was also a very strong Nazi, but without him, we wouldn't be here, probably. I just want to know, I personally think no names should ever be raised. You should just stick with it. And I just wanted to know what other people, in case some other people wanted to start to remove the word Wagner from the literature. I think it would be a great shame, but if they want to do it, well, we might have to think about that. Maybe everybody will think like me that we should stick with it, but I just raised the issue.
Is it, Peter, is Aberdeen far enough from Oxford and the other centers to still stick to some names? I don't know. But
I'm wanting it to be a scientific discussion, not a sociological.
Yeah. But John, I'm not sure that he was Nazi. How you know this?
Oh, it's very well documented. He worked throughout the war, and he was taken to the United States immediately after the war to give advice on seaplanes and things like that. And it's clear that he was quite a committed Nazi.
Oh, okay. Yeah. Very complicated question. Peter, is much more complicated than mathematics.
It's not really a question. It's just.
It's not really a question. Yes, it's not a question, but
the way we talk about our research, because we wouldn't be able to talk about Wagner theory, which would be. Well, what would we call it? I don't know.
Yeah. Mark Cooker. Mark.
Hello. Thank you, Peter, for a super talk. I just want to add to what John has just said. I have very mixed feelings about the ethics of all this. I think one answer to it is to continue to call it Wagner theory, but to also make sure that the factual historical background is better known. I've only a few months ago came across something that I found frustratingly incomplete about Wagner's Nazi background, and I just wish I knew a little bit more. Apparently he was debriefed by the Americans after the war, and I'd like to see or know a bit more about what their debriefing involved. So I think we need all of it. That's my view.
Personally, I know nothing about this part of the story. Personally, so just nothing. I only know that the Wagner published paper in 1957. From being already in US, but what he did, it's something like about acoustics or dynamics. So it's and nothing else. So John, if I don't know, if you sent me or us some links or
no, I've read various articles in various places, but I suspect the debriefing that Mark mentioned is highly secret, because he was working on, I presume he was probably working on things like impacts of rockets and things like that, as well as he started off with seaplanes, didn't he? In 30.
Yeah.
And I imagine he was still doing bouncing bombs. Goodness knows what he might have been doing during.
Okay, yeah. But it's we can decide or conclude or for ourselves. I believe only if we have evidences of that. Yeah. So as to me, I just didn't so far come across any papers on Wagner. Just no papers. Just the paper from 1932 and the paper from 57, which I don't know what it's about. I don't remember. It's definitely not about impact. So that's all. So this is the only what I know. So it's not enough information to conclude. But John, it's kind of likely to be the case. But likely to be. But it could be. Is it possible, kind of, to separate scientific contribution and kind of the political.
I think that's what Mark is suggesting, and I thoroughly agree with that.
Yeah. So the kind of Wagner theory and what he did, it's one big story. But yeah, on the other hand, just a moment. On the other hand, I remember that it's still in use. It's called Atlas for anatomy atlas.
Mm-hmm.
Which was partly done in concentrated camps.
Mm-hmm.
Because they had the chance, to have that material, say. But interestingly, the quality is very high. So I believe it was about 2-3 years ago article on BBC. I mean, online, that the quality of the object is still the best one. Even it's from 40s, and the people use it, and in particular, I'm sorry for that, but in particular, Oxford University was mentioned that it's still kind of recommended and still used, and the students. It seems that some students were concerned: is it right that we are using this atlas, because it was the picture there were received is not in acceptable way. Yeah, so there is a point, right? Yeah, but very complicated.
But that was not personal names. So here,
no, it was no. It was personal, because it was just one doctor who guided all of them.
Okay.
Sorry?
If it was only one person, it is similar. Then.
Yeah, but there were many people actually who was a team for doing this, because it's amazing how they did it. But on BBC they gave a kind of picture of this person, and they said he was the real Nazi. So he worked in that their dress, and yeah, so it's very complicated, but. It was more clear with that atlas on anatomy, but it's still the problem that it's useful. It's still helping doctor to surgeon to in surgery to save life of people, but it was obtained in not acceptable way. I mean that all pictures. Yeah.
Well, if we all have the same general sort of attitude, I think that's very helpful.
Yeah. So it's very complicated.
Others saying one thing and others saying another, and it sounds as if.
Yeah, and it's not only different people saying different things, but each people has a kind of several sides of the story. Right, so it's always something there could negative, positive, and yeah, very complicated.
I mean, I confess I'm ignorant about those particular aspects. That's something I should take away and find out more about myself.
Yeah,
because it's something we use.
Yeah.
I'm struggling without more information to make an informed judgment about that, but it certainly is obviously important, and we need to think about that as a community.
Well, the stark one seems to be the people who want his name removed altogether are administrators and people like that, and the physicists want to keep it, obviously, because it was a very important development in quantum mechanics.
Yeah. Peter, could you see chat, by the way?
I can see the chat, yeah. I've got the chat.
And also it will be with you, right? Because there are some, like Mark Cooker is suggesting you to include growing cavity on the vertical side of the wall. I mean, on the edge, on the corner point, you satisfy the condition that the flow is tangential. But then it's a kind of return and close cavity on the wall. It's possible. By the way, I have slides on this topic somewhere. John, you could remember in 2008, it was a conference, Free Boundary Problems in Stockholm. Yeah.
Vaguely.
Way long time ago, right? So
So just
Peter, if I find the slides, there are no paper on it, just slide. So I'll send you.
So just to confirm, you're talking about something that looks like there's a step, that kind of cavity or something like that. Is that what you mean, or does that look right?
Could you show?
Can you not see that? What have I managed to do there?
No, I can see only your background. Yeah.
There we go.
Yes.
Sorry, this modern technology and this dual mode teach, I'm getting right eventually.
Fine. And also Robert suggesting to consider the same problem, but without the vertical wall. It's a plane.
Yeah, I mean, the sort of flat plate here.
Flat plate, and also on one slide you showed step and impact not at the corner, but at distance from the corner, right?
Yeah.
And that is also interesting. So it's like impact on the flat plate, but then suddenly there is the end of the plate.
Yeah.
So what's happening there? How it's developed? So that is interesting. I don't know what would be there.
I did gloss over that, right? Because obviously, the flat plate solution, your pressure is, while it's on the flat plate, you have your outer solution has an unbounded pressure at that contact line, which suddenly immediately just vanishes when that contact line passes over.
Yes.
And that looks a bit odd to me. And there were a couple of features like that. Also, your pressure on the inner contact line where you have these two contact lines is unbounded, and then the contact lines come together and that middle bit then just disappears. So there were some details in there but the middle for the contact lines coming together, obviously the air in there gets to become important at some point.
Yeah.
But it is worth, I think, just looking at how the contact lines do combine at that one.
Yeah, Peter, and could be what the Mark suggesting about the cavity. It's actually about the air effect. Yeah, it could be without air, it could be different. But it's also interesting to, as I said, to do experiments. Could be in a larger scale, but scaled conditions of experiments to see what's actually happening there. Yeah, that would be interesting.
In the steady flow, it would be a 3/2 singularity there, wouldn't it?
Yeah.
Does that start as a 3/2, or does it take a little while? Is it a function of time which starts from 0 multiplying z to the 3/2?
Yeah,
that would be interesting to find out.
Yes. So thank you very much, Peter. So that is the okay. I cannot say the discussions lasted as long as your presentation, but this is, I believe, the longest discussion so far.
Well, that's good. Keep you occupied. Something to think about.
Yeah. Thank you very much, all participants. Thank you very much, John. Thank you very much, Frank, and Peter. Definitely, it's your time and your lecture which made this day so special. Okay, so then I close the seminar. I will still stay, but I switch off my camera and microphone. I'll stay. I should stay to download the record, okay, and then it will be available hopefully if technology works fine. Okay, thank you very much. Yes. Thank you very much. Thank you very much. Bye.
Thank you, everybody. Expect to see you all.
Next week it's also interesting presentation, but about other stories, but also from former students supervised by Mark Cooker. Okay. So bye.
Bye, everybody.
Bye.